Okay, and our second speaker for today is Bruno Bento from Liverpool, and he will talk about gravity at the tip of the throat. Please go ahead, Bruno.
Hello, everyone. First of all, let me thank the organizers for giving me the opportunity to be here and to talk about the work that I've been doing with Dibia, Susha, and Yvonne, and which should be on the archive tomorrow. So keep an eye out if you want to know all the details. The work is all about extra dimensions and gravity. And the ultimate goal would be to detect these extra dimensions if you start from this fact that string theory includes extra dimensions. And with the recent success of LIGO and other detectors in detecting gravitational waves, a very natural question to ask is whether you can use gravitational waves to detect these extra dimensions. And to actually address this question, we need to understand how gravity looks like in 4 dimensions when it arises from a higher dimensional theory. And it usually turns out that the effects that come from these extra dimensions appear at very high energies, at very high frequencies in the language of the gravitational waves. And it becomes really hard to detect these signals. And this is exactly where the warping can be useful. Usually warping is used when you have a very high energy scale and you want to bring this energy scale down to more accessible energies. And they are very, very common in string theory compactifications. So the first thing you want to ask is, how does warping affect your gravity in 4 dimensions? So before I start, let me just mention some work that's been done on this, in particular, using gravitational wave signals as a way to detect extra dimensions. The warping itself has been explored mostly in the context of Randall syndrome, but more recently in these works in the context of toroidal compactifications in string theory. And I'm sure there will be more work which is very interesting on this topic. So I apologize if I'm not mentioning your favorite or even your own work. So please let me know if that's the case. I would love to look at those. I should definitely mention these 2 works down here because they are the ones that we use to extract the experimental constraints, which we compare with our predictions, as we will see very soon. So that being said, how does the 4-dimensional theory know anything about the higher dimensional one? I think this picture is very nice in giving us some intuition of what's going on. So even though it's probably familiar to most of you, I decided to keep it in. And the idea is that the momentum along the extra dimensions will look like a mass term in 4D. And because we usually consider compactified extra dimensions, this momentum will be quantized. And so the masses that you see in 4 dimensions will also be quantized. And this is exactly what gives rise to this massive tower of modes, which goes by the name of Klutz-Klein tower of modes. And this is the signature of the extra dimensions in your low energy 4-dimensional theory. Usually what you want to do is to make this tower very massive, such that the modes, the tower of massive modes, is way above the cutoff of your effective field theory. And so anything that you can do, anything that you can probe, will just miss the massive modes. But if you want to detect the extra dimensions, what you want to do is to see this tower of modes. And so you actually want to include some of these modes into your effective field theory and be able to probe them with the energies that are accessible to you. So one way of doing this is just to move the cutoff up, which should be accompanied by being able to access these high energies. And another way to do it would be to bring the tower down, such that some of the modes are included in the effective field theory with a cutoff which is compatible to what you can currently or in the near future probe with your detectors. And this is exactly where the warping comes in. In string theory compactifications, you usually split the 10-dimensional spacetime into a 4-dimensional spacetime and a 6-dimensional internal space, which will determine many aspects of your low energy 4D theory. And this is the theory that you should ultimately try to connect with observations. And in flux compactifications in particular, it is very common to also have some warping. And the warping will come, it will show up in the form of this warp factor multiplying both pieces of the metric. And intuitively, what the warping does is deform your internal space such that your space develops these warp throats, these warp regions. And on the side of the 4D theory, on the 4-dimensional spacetime, it will affect and warp down the energy scales. The easiest way to do it, to look at this, is to look at the momentum squared using this 4D metric. And you see that you get this warped mass, which is a warped down version of the mass with which you start in the fundamental theory. In our particular work, we use a Klebanov-Strassler solution for type 2b supergravity. This corresponds to a warped deformed conifold, which is a good description of this warped throat in the compact space. And so the internal space with which we are going to work will consist of a Calabi-Yau, which is not warped, and then it will have a region which is well described by this warped throat. And for convenience, we also include a region which is some kind of transition between the warped throat and the Calabi-Yau, which is described by the unwarped deformed conifold, just so you can have a metric which you can explicitly use in computations. Very well, this gives you the background of your solution. This is essentially the vacuum expectation value of the graviton. But if you want to look at interactions, that's gravitational interactions, you actually want to look at the fluctuations around this background. And because it is a 10-dimensional field, the graviton itself will give rise to a massive tower of states, which will be the signature and encode the extra dimensions that we want to detect. So what we do in this work is derive the equation for these fluctuations, which is essentially a wave equation for the 10D graviton to linear order. And the equation will depend on the curvature of the background and on the energy momentum tensor of, in our case, the matter fields in type 2b. And the derivation of this equation was done very recently, for a d-dimensional Einstein gravity with a cosmological constant, also in the context of exploring gravitational waves as a way to detect extra dimensions in this work right here, which is very nice to compare the results. So what we want to do is to study the 4-dimensional effective field theory, which means that actually from this perspective, the 10D fluctuations that I'm talking about will include not only the spin-2 modes in 4D, which are the gravitons in 4D, but also the vector fields or the vector modes and some scalar modes. And these are the famous scalar degrees of freedom, which give rise to the module that people try to stabilize all the time. And we could naively look at this and think that just from counting the degrees of freedom naively, you would get 21 scalar degrees of freedom. And that's just because you could think of this as a 6x6 matrix, it is symmetric, and so you'd get 21 scalars. So why don't you actually have 21 moduli in all compactifications that go from 10D down to 4D? Well, the reason is that if you want to look at your 4-dimensional theory, you need to not only decompose the wave equation into a 4D piece, which is the familiar kinetic term for the 4D theory, and a 6D piece, which looks like a mass term, and it will actually give us a mass term in the 4D theory. But you must also decompose those fluctuations, which were 10-dimensional fields, into 4-dimensional fields and wave functions, where the 4-dimensional fields only have 4-dimensional indices and depend on 4-dimensional coordinates. And then the wave functions will encode the higher dimensional information, the information about the extra dimensions. And so these wave functions will constitute a complete set of functions, a complete basis of functions, which depend and are determined by the 6D Laplacian associated with the space that you chose for your compactification. This is the eigenvalue equation that you need to solve. This will give you not only the wave functions, but also the masses, which will appear here, as I mentioned before. And the moduli that we usually talk about and that we want to stabilize are the solutions to this equation associated with the scalar degrees of freedom, which have mass equal to 0. So essentially, they are the massless fields that you need to include in your theory, even if you want to integrate out the entire massive tower. And the number of these moduli will depend on the number of solutions, which in turn depends on the Laplacian and the space that you chose to compactify. So going back to the graviton, what we actually did was use this equation to and solve it for the 4D spin-2 modes and using the Klebanov-Strassler solution, which gives you an explicit metric with which you can actually make explicit computations. So let's look at some results. I should mention that this was also done in these two works here, although the emphasis is very different in each of them. And I should also say that we are using the symmetries of the conifold to express the wave functions simply as a function of the radial direction. And this is similar to what you would do for the hydrogen atom if you ignore, if you look just at the energy levels and ignoring the different types of orbitals. Okay, so in terms of the results, on the left-hand side, I'm plotting the mass of the first massive state, which essentially gives you the Kaluza-Klein scale, the warped Kaluza-Klein scale, as a function of the strength of the warping. And we chose to parameterize the strength of the warping using this parameter, tau c, which is essentially the value of tau where the throat will glue to the bulk, where the warp factor becomes negligible or order 1, and so you don't have warping anymore. And what you can immediately see is that the stronger the warping, the lower the masses that you get. And so stronger warping will bring the Kaluza-Klein scale to lower and lower values. On the right-hand side, I'm showing you the wave functions for the first 3 modes, for the first 3 excited modes. And there are 2 things that you can immediately see. First, you see the localization of the modes near the tip of the throat, which is at tau equals 0. And second, you see that higher modes will have wave functions with higher amplitudes. And this is exactly what's emphasized in this work here, although in our case, it won't be so relevant. But it's a quite interesting feature of the Klebanov-Strassler solution, which, by the way, you wouldn't see in the Randall-Sundrum scenario. So in a second, I will try to explain how these properties, namely the suppression of the masses, the localization of the wave functions, and the actual amplitude of the wave functions will translate into the interaction in the 4-dimensional theory, the gravitational interactions in the 4-dimensional theory. So just as a quick aside, something we explore in the paper as well is this competition between the strength of the warping and the size of the bulk. So if you compare these wave functions that I just showed you on the right with these wave functions, you see that they try to localize, but then you reach this plateau and they try to spread as much as possible throughout the bulk. And this is because if the warping is, if the bulk is too large, if the compact space is too large, then it will be this volume which will dominate over the warping. On the left-hand side, I'm showing you how the masses behave if you fix the volume of the compact space and then just change the strength of the warping. You get a constant value for the masses until the warping starts dominating and you get this suppression. This was also mentioned in one of those papers that I just showed you, but it's especially interesting when you interpret it in terms of the effects on the gravitational interactions in 4D. So let's go back to that story. Let's imagine that we are living on a brain located somewhere along the throat. And what we want to do is to look at interactions, at the gravitational interaction between matter which is confined to the brain. This matter will be described by this energy momentum tensor here. And from the 10-dimensional perspective, what you're doing is just exchanging the massless 10D graviton. However, as we saw from the 4D perspective, what you're actually doing is exchange an infinite tower of massive modes. Well, one of them will be massless, all the others will be massive. And crucially, the way these modes will couple to the matter on the brain will depend on the wave functions of those modes evaluated at the position of the brain. And this is very important because, as we saw, the wave functions decay exponentially fast as you move away from the tip of the throat. So if I choose to put my brain away from the tip, these couplings will be very suppressed compared to what you would get if the brain was at the tip of the throat. And this is something we are going to explore when comparing with experimental and observational constraints. You will also have, as we mentioned before, a suppression of the energy scales on your brain theory. which will be dictated by the strength of the work. So the important question is, can you actually see the extra dimensions in practice? Well, this plot summarizes the experimental and observational constraints for Yukawa type corrections to the Newtonian gravitational potential. And what I mean by this is that you can use the setup that I just described with the massless mode and the tower of massive modes, compute the gravitational interaction, and derive the Newtonian or the classical gravitational potential, which will give you, for the massless mode, the usual Newtonian result, plus some corrections, which you can parameterize using this Yukawa parameterization. And this is very nice because a lot of experiments were, the results to a lot of experiments were expressed in this language. And so it's nice if you want to compare your predictions with the results from those experiments and observations. So this alpha right here will encode the strength of the interaction and the correction. And this lambda right here will encode the range of the interaction, and it is associated with the mass of the particles being exchanged, which in our case will be the masses of the KK modes. So in practice, what this means is that you can compute explicitly these parameters, which are probed experimentally, in terms of parameters of your string theory. In this case, parameters which appear in the Klebanov-Strassler solution. And in particular, I'm talking about the string coupling, the flux number m associated with the conifold, the position of the brane, tau b, and this hierarchy, which is the hierarchy between the UV scale, which we will take to be the string scale, and the energy scales on the brane, which we will fix to be the TeV scale. And because you have this mapping, you can actually use the several requirements for control of your theoretical framework. In particular, you can use the supergravity approximation or alpha prime expansion. You can use the string loop expansion, or the fact that these should be under control, and the fact that you need to cancel the D3 tadpole, such that you get some bound on the flux numbers in order to restrict the parameter space of your predictions. So what does this look like on the plot? Each position, so if you choose to put the brane at a specific point, in this case tau b equals 0, these conditions will restrict your parameter space to this small triangle right here. And then if you move the brane, what you're doing is moving this triangle of allowed parameter space throughout the plot. So the first thing you can see right away is that the allowed regions never intersect the excluded region of parameter space. What this means is that with the available data, with the current available data, you cannot exclude any of these examples. And of course, I should mention that we are fixing the hierarchy, and this is a huge factor in my claim that you cannot exclude them. The second thing, and maybe even more importantly, is that the position of the brane is crucial to the prediction of this allowed region. You see that if you bring the brane, if you pull the brane away from the tip of the throat, it will not only allow you to have lower masses for the KK modes, which will translate in larger ranges for the interaction, but it will also suppress by a lot the couplings of your corrections. And what this does for you is that even if you increase the masses, instead of going head straight into the excluded regions, you actually avoid them by going down in terms of couplings. And this is especially interesting if you're interested in gravitational wave detection. And the reason is that each mode in the tower of massive states will have its own wave equation, like this. In particular, when an event generates a gravitational wave, it will do so by exciting the 10-dimensional graviton. But because this graviton is decomposed into all these modes, what you're actually doing is excite all those modes in a very particular way. And the big difference between exciting a massless mode and exciting a massive mode when it comes to gravitational waves is that the massless one will have the gravitational wave associated with the massless mode will have a frequency which is determined by the event. So if this event is a black hole binary, the frequency will be determined by the black hole binary. However, and the properties of the black hole. However, if you're exciting the massive modes, the frequencies will actually be determined by the masses of these modes. And so if the masses are very high, you get very high frequencies, and you're not able to detect them with current or near future detectors of gravitational waves.
Bruno?
However, if you can bring these masses down, what you're doing is bring the yes.
You have 5 minutes.
Thank you, great. So if you bring those down, you bring the frequencies down, and you can hope to put the new signals into the window which is probed by any of the current experiments like LIGO and Virgo, or the planned experiments to the new, hopefully the near future, LISA and the Einstein telescope, and even some experiments that have been discussed recently that could probe ultra-high frequency gravitational waves. So this is what we did. We tried to explore the parameter space in our setup and try to find examples which would bring these frequencies down to these windows associated with each of the experiments. And the first thing that you see is that indeed the masses of the KK modes need to be very, very small. And so the first thing that you would think when you look at these masses is, if they are so low, then you probably would have detected them at some point with some other experiment, which is exactly why we spend so much time looking at these experiments and at these constraints. And it is the coupling becoming smaller that allows you to avoid this detection, even for very low masses of the KK modes. Secondly, you notice that the tadpole contributions that we need, which are associated with the deformation modulus, which in turn determines the strength of the warping, is very, very large. And this brings us directly to consider the tadpole conjecture. And it would be very important to understand if we can have tadpoles which are this large, or if it's inconsistent with the compactification, because that would immediately change the whole picture when it comes to the warping. And finally, it's also important to understand how the wave functions, which were so important in avoiding the experimental constraints from the other experiments, will affect the signals from gravitational waves. We would expect them to also be suppressed by these wave functions. And so it's important to study carefully and to see exactly how these will influence the signals. And in particular, we would like to explore whether localized sources, which would be more similar to the brain situation that I showed you before, and extended sources, which would probably couple more strongly to the KK modes, how they would differ in terms of the gravitational wave signals that you get. And we'll leave this for future work. And it's a very interesting question. So let me just conclude. The main thing, or one of the main things to remember, is this connection between the extra dimensions and the tower of gravitons in 4D, which in turn translates into a tower of gravitational wave frequencies. What we were able to do in our work was to map the parameters which are probed experimentally in other experiments with the parameters involved in the Klebanov-Strassler solution, and try to understand whether lowering the masses as much as you need would actually be in conflict with the other gravitational experiments. And what we found is that actually, because of the couplings, this doesn't happen. You don't bring this, there is no conflict with the current experiments. Something that will be very important will be to explore the effects of the wave function profiles in the gravitational waves, which brings us back to that discussion on the localized versus extended sources. And we should also not forget the relation between the strong warping and the large tadpole contribution, MK, which is leading directly to the tadpole conjecture and to the question of whether this is consistent or if we cannot use warping like this. So this is all from me. Thank you very much. And ask any questions. I'll do my best to answer them.
All right. Thank you very much, Bruno, for a very nice talk. Are there questions? While people are thinking about questions, maybe I can start with one. Can you go back to the exclusion plots?
Yes.
Yeah. Good. So just from looking at this, so let's say the tadpole conjecture is true. So then looking at this, the best shot I have at dipping into this would be sitting at the tip of the throat and having stronger collider bounds. This seems the closest, but so how much would the collider bounds move if I was to build, let's say the next generation LHC 100 or whatever?
Yeah, so actually I don't know exactly. So you have to move a little bit in energy, but it would also help to move in luminosity to probe lower couplings, because so we have this point here A, which are just some, you choose some reasonable parameters, and by reasonable I just mean away from the boundaries of control. And you see that actually if you just go up in energy, you'll miss the point by a tiny bit. So you need two things, the two things, the higher energies and the higher luminosity. And so it's not so clear. I don't know exactly what this means in experimental terms, how far we are from that. But even if the tadpole conjecture is true, then I don't think you can even get to this point. You basically go back to getting the hierarchy from large volumes and not from the warping itself, because the warping, if it's to be within the constraints of the tadpole conjecture, the warping will be very, very small.
Okay, thank you. Are there further questions? Yes, Severin.
Hi. I have a question, namely, there was an old paper by, I think, Berg, Haag, and Mock, and they computed the spectrum of spin 2 excitations in a Klebanov-Strassler background. And I think their motivation was more for holography, so they looked particularly at the non-compact Klebanov-Strassler solution. Do you know how that relates to your Graviton spectrum? Because it seems to be something similar. It also seems to be a spectrum of spin 2 excitations.
So which one did you say? I don't think I know this one.
By Berg, Haag, and Mock, I think from 2006, something like that.
I think I don't know it. I don't know exactly what to say about it. So the one we saw that does exactly this is this paper by Tai and Firujai from 2005. But they also get the spectrum of KK modes with the Klebanov-Strassler solution. But then they're interested in tunneling through different throats, between different throats, in the context of reheating. But I don't think I know the one you mentioned. So
okay, yeah, never mind. When you compute the spin 2 spectrum, do you look only at like the 10-dimensional graviton, like expanding the action of the 10-dimensional Laplacian on the 10-dimensional metric, or do you also take into account the coupling to all the other fields in the Klebanov-Strassler?
Right. So yeah, initially we take the type 2B action with all the bosonic fields. We derive the equations of motion for the graviton, which includes the couplings to those fields as well. But then in order to get the spectrum, we actually simplify by putting all those fields to 0. So one of the next steps would be to try and keep some of those fields and see how the couplings would affect the results. And in particular, there is, so in this work that I mentioned by Andrio and collaborators, so this one, there is an effect which you can only see if you keep some of those couplings. So they identify this breeding mode with an extra polarization to the gravitational waves, which you can only see if you don't do what we did, which is set the fields to 0. So there are some effects that we are missing by doing this.
Okay. Yeah, I think you might want to have a look at this paper I mentioned, because I think they in principle compute the honest spin 2 spectrum on the Klebanov-Strassler.
Yeah, I'll definitely have a look. Yeah, thank you.
Okay, thank you very much.
All right. In the interest of time, let's close here and thank Bruno and also Anthony again for their very nice talks.
Thank you for having me.
And we'll see you next week. Bye.